We're going to go over Young's modulus, bulk modulus, and also the shear modulus in a very simple way. So starting first with the Young's modulus. What is it? What does it talk about? Well, we need to know the other name for Young's modulus is also called modulus of elasticity. And so, what is this one? Now, Young's modulus is simply the ability of a material to withstand changes when it is subjected to lengthwise compressions. And so, let's say we've got a wire here. And it is, let's say, on a table. Yeah, this is a table here, and we get to attach a certain mass at this point. And we've made sure that it is strongly held at the very end here such that it will not be able to break free. And so as you get to increase the mass, this thing is going to be put in this direction. So it is not moving from this point of attachment, but it is being pulled in this direction. In other words, there is a certain increase in length. And so that is how we are able to determine Young's modulus. We can determine Young's modulus for such a material when that is happening. Now, for Young's modulus, the force that has been applied is applied to a certain material perpendicularly. So, just like I'm demonstrating here, when you have got this end point and you get to attach a wire, so this is the wire that we've attached. So we have attached this wire at the very end of it. We have attached a certain mass which has got a weight. So we say it is attached. So we've attached this mass perpendicular to the wire. So the force is pushing in the down direction, and there will be a certain increase in change in length. Now we need to understand some words here. Young's modulus, of course, the symbol here is capital E. Of course, some books are going to use Y, but most are going to use capital E. And Young's modulus is given by tensile. Tensile has to do with a compression or something that you are pulling or pushing, increasing length. So that is tensile stress divided by tensile strain. And well, the symbols here, stress, the symbol is sigma, and the strain, the symbol we're going to use is also more like an E, like that. But what are these? What is stress and what is strain? Well, stress is simply the force that you are going to apply to cause a change in the shape of an object or the length of an object. So that force that you have attached, so that there will be a certain change in this length. That is what we call stress. Now, strain is the actual change in length when you apply a stress. So that is strain and that is stress. But how do we get to calculate stress? So sigma, that is stress, is given by force over area. And the strain, which is the tensile strain in this case for Young's modulus, is simply given by change in length divided by original length. Now, when you had a wire like this one, there's a distance from that point to that point. When you get to apply a stress to this wire, the length is going to increase. There will be a certain increment. So this increment at this point. So we see that whenever you apply a force, the length that you get at the end is always much bigger than the length that you had at the beginning. So that is one thing that you also need to get. But another thing as we get to talk about Young's modulus is, as the length is getting to increase, the radius is getting to reduce. So think of a material. I'm going to draw a material that is more round. Take this as a wire, not as a cylinder. So this is a wire and it has got a certain radius there. So as you get to apply a force, putting it in this direction, when you apply a stress, Well, the length is going to be increasing in length, but it is going to reduce in diameter, and because it has reduced in diameter, then it has also reduced in radius. So it becomes something like that. So this is the actual length, the actual radius I can give it cap to r, and then the final radius I can give it small r. So we have got a change in radius here, and the change in radius is always going to be negative. And the reason of being negative is because the actual one is always smaller than the original one. And because of this, and so let's take this. We have got first the original length at this point, and then there'll be a certain change in length. Maybe the original just gets to end up to this point. This is the original length, and then one of this new one which is present here. So this is the change in length. And same, this is going to be taken as the original radius, and this small r which I've named as small r, there'll be a certain change in radius, and let me call it the same change in radius. Okay, so here for a rod like this one, the tensile strain which we can see here, we know tensile strain is given by change in length divided by actual length. This tensile strain is called linear strain. And there's also the strain that arises by change in radius. And so that is going to be the strain which is coming by change in radius, that is going to be given by negative change in radius divided by actual radius. Why am I saying negative? That is because the change in radius is always negative. That is because the final is always smaller than the initial. That is why the negative there. So it's always going to be negative. And this one, this is called the lateral strain. So when we are using change in radius, that is called the lateral strain. And so we can also define the Poisson's ratio if we know the linear strain and also the lateral strain. The Poisson's ratio, which is given by the symbol mu, is actually equal to lateral strain divided by the linear strain. So that is the formula, and we know what lateral strain is. We can get to substitute where there is lateral strain, we get to put this one, and then where there is linear strain, we can get to put this one. So that is what we can do. Well, this is about Young's modulus. Let's also consider another property of material, which is the shear modulus, and then we can get over some practice questions. We have said Young's modulus is also called modulus of elasticity, but shear modulus is also called modulus of rigidity. So that is the other name. Well, what is shear modulus? So this is simply the measure of the ability of a material to resist transverse deformations. So when you've been given a certain object like this one, so when you are talking about shear modulus, we don't apply a force perpendicular, we apply a force parallel to the object. When it is Young's modulus, the force is applied perpendicular to the surface of the object. So we are going to apply a certain force here, and there will be a force which will be moving also in this direction, such that this thing is going to change shape in this way. So it moves lines. So if this is the actual length here, there will be a change in length. Of course, this is also the actual length in this direction. So considering from where it was at the very beginning, there is a change in length here. I'm using x, I could have also used L. So that is the change in length that we have, and we have got an angle theta here. Okay. And we can also have, let's say we've got a rod which is on a surface. And now we get to apply a force at this point, which in this case is a stress. A stress is a force that causes a deformation or a change in the shape of an object. And so this thing is going to also get to strand. That is how it's going to become. And so even for this one, there's a change in length from where it was to where it has gone. So that is about shear modulus. And shear modulus, we use the symbol G. Shear modulus is given by shear stress by shear strain. Well, the formula for stress and strain remains the same. Stress is force over area. Strain is change in length over actual length. So that is the formula also for this one. Now, the last one we should understand is bulk modulus. So bulk modulus is simply the ability of a material to resist changes in its volume. Say you get this sphere. When it is just in the atmosphere, subjected to just influence of the atmosphere, it has got, there is a certain pressure being exerted on it by the atmosphere. So we're going to call that as the initial pressure. And so when we get to take this same sphere into a river, so under the river is going to be subjected to a certain force because the waters also have got a certain force that they'll be exerting. Remember, there are hydrogen bonds in water, and water molecules always tends to come together each other. So if we've put this one now in water, so the water is going to be exerting a force on this one, such that by the end of it all, the shape of this object is going to reduce. So it has first an initial volume at this point, but the final volume here is going to be much smaller. Why? Because it is reducing in shape. It was bigger initially when it was in the atmosphere, but now when the pressure was changed, so at this point we have got a final pressure, and at this point we have got an initial pressure and an initial volume. So to define bulk modulus, the symbol is B. It is given by volumetric stress over volumetric strain. And stress is simply given by force over area, and strain is going to be given by change in length, in this case not length but volume, change in volume over actual volume. But because the volume is always becoming smaller, so we always get to attach a negative here because the change is going to be negative. You can think of it, final is small, initial is big, so it will always be negative. Now force over area, because we are talking of liquids mostly for bulk modulus, force over area we know that is pressure. So this is the same as pressure divided by negative change in volume over actual volume. But this pressure is not just pressure but change in pressure, because it had a certain pressure at the very beginning in the atmosphere, and then there is a certain pressure that the waters are exerting on that object. So that is a change in pressure. Alright, so that is it, and let's get to look at some practice questions. And the first question we have here: a rod has a cross-sectional area which is 2 times 10 to the power negative 3 meters squared and a length of 1 meter, and is made of brass with a shear modulus of 36 times 10 to the power 9. So this is 10 to the power 9 Newton per meter squared. How large should the shear force exerted on each edge of the rod be? So what we're talking about is we have got this rod like this. When we get to apply a force here, of course there should also be a force which will be balancing such that this thing doesn't just move linearly. So it now changes shape, Okay, something like that. And then we're going to have a certain change in length here. And remember, there was an actual length, the length of the rod, which is simply its height. Now we want to find the forces which we are going to exert at this point and at this point. Well, that should be the same force that we're exerting. Now we know that the first thing is, how large should the shear force be? That is the shear force. Okay. How do we get to calculate the shear force? Well, we're talking about a shear here. We know that shear force, or shear stress in this case, that's a force, is given by force over area. So the shear stress is given by force over area. And we only know the area, we don't know the force. This is the force that we want to understand. So this will be force over, what is the area? We've been given the area there as 10 times 2 times 10 to the power negative 3 meters to the power 2. And so just take that there is a 1 here, so that we say 1 divided by what is in the denominator. And that is going to give us 500. F is still there, so we just keep the F there. So that is how we get to find the shear stress. But we also know there is a certain change in length, dx. Dx is, I could have also written it as delta x, that's the same change in length. We can also determine the shear strain. And we know shear strain is given as dx over x, or change in length over actual length. So the change in length in this case is 0.02. But remember, this is in what? Centimeters. So we need to convert it to meters. And how do we get to do that? Centimeters. So we're going to multiply. We know that in 1 meter we have got 100 centimeters. So that the centimeter and the centimeter cancels. And then we're going to divide by the actual length of the rod. What was the actual length of the rod? 1 meter. So we see that this meter and this meter is also going to cancel out. And so shear stress is unitless. And when we get to punch this, we're going to get 2 times 10 to the power negative 4. There's no unit there. And now we can define, we've been given the shear modulus. Of course, shear modulus, that is G. Shear modulus is given by shear stress divided by shear strain. And the shear, first we're going to substitute the shear modulus, which is given, that is 36 times 10 to the power 9. And the shear stress is here, 500F, divided by the shear strain, which is 2 times 10 to the power negative 4. So at this point, I'll say this is over 1 and I'll cross multiply. I'll multiply this by that. And I just want to remain with F, so, and then divide both sides by 500. So that is going to be 500F being equal to 36 times 10 to the power 9, and that is multiplying 2 times 10 to the power negative 4. And therefore divide also by 500 both sides. Therefore the force which is to be exerted on each edge is going to be 14,400 newtons. And that is the force. Let's consider question number 2. A pendulum consists of a big a sphere of mass 30 kg hung from the end of a steel wire. So say this is a steel wire, and then we have got a certain mass here. Okay. And this wire is 15 meters long. Well, this is not a rope as we use for common pendulums. This is a wire. Now, so we get to have a pendulum consists of a sphere. So that's a sphere, and it has got a radius of 0.1693 centimeters, and the Young's modulus. So as I said, Young's modulus times they use Y, at times you find E, but mostly we use capital E for Young's modulus. So we want to find the tensile stress and also Okay, just the tensile stress that is on the wire. But how do we get to calculate the tensile stress? We need to know that tensile stress is given by force over area. And the force is what we are actually looking. No, we are not looking for this force. We are looking for the tensile stress itself. Okay. So what is the force on this object? What is the force being exerted on this wire anyway? Force is also, we know that force is equal to just a weight, because we want a force that is going to cause a change in this length. So force is also given by mass times gravity and then divided by area. And the mass for this one is 30 kg, g is 9.8. But how do we get to find the area? We know that area is given by pi r squared. So this is going to be pi. What's the radius? Now, if we consider also the radius has been given in centimeters, we need to convert that to meters. And how? We get to divide just by 100. So that would be 0.1693 divided by 100. So that would be the radius. And then we are going to get to square that. So let me see what I'm going to get. 0.1693 divided by 100. I'm starting with the denominator, and then I get to square that answer. I multiply it by pi, and then on top we have got 30 multiplied by 9.8, and then we'll divide by what is down. So that is going to give us area, which is, let me just get to punch that again so it will be good. 0.1693 0.1693 divided by 100, and then we square that one, also multiply it by pi, and then on top, okay, so I've actually calculated the area down first. So on top we are going to still have 30 multiplied by 9.8, and then down we have got an area 9.00 times 10 to the power negative 6. And so this is going to give us 3.27 times 10 to the power 7 Newton per meter squared. The area is in meter squared. The force is in Newton. So that's why the unit for tensile stress is in that one. So we've determined the tensile stress. The other question, and the increase in its length. So we want to find the increase in the length. In other words, the change in length. What is going to be the change in length? Well, we know that Young's modulus is given by tensile stress divided by tensile strain. And I'll get to substitute the Young's modulus, which is given there. Before then, let me first write also the formula. So we already know the tensile stress, so I'll not substitute a formula there. But what I'll do is I'll substitute a formula for tensile strain. How do we get the strain? Strain is given by change in length over actual length. And so where there is capital E, which is Young's modulus, I'm going to put 200 times 10 to the power 9. And that is going to be equal to, where there is sigma, which is tensile stress, I'm going to put 3.27 times 10 to the power 7. And then divided by change in length over, what was the actual length? Well, this wire was 15 meters before, so that will be 15. So I'll multiply this with that. So that is going to give us 200 times 10 to the power 9 change in length over 15, and that is going to be equal to 3.27 times 10 to the power 7. So to remain with change in length, I'm going to multiply everything. We have got a 15 in the denominator, so I'll multiply by 15. And I also want this one not to be there, so in the denominator I also put 200 times 10 to the power 9. And so the change in length is going to be 3.27 times 10 to the power 7 multiplied by 15, then divided by 200 times 10 to the power 9. And this is going to give us 2.45 times 10 to the power negative 3 meters. So that is going to be it for this question. Let's consider this one also. A cylindrical steel rod has a length of 2 meters and a radius of 0.5 centimeters. A force of magnitude 2 times 10 to the power 4 newtons acting normally on each of its ends. Find the change in its length and radius if the Young's modulus is given as 200 times 10 to the power 9 newton per meter squared and the Poisson's ratio is 0.25. So how do we get to work out this? Well, what are they trying to ask us about? Want to first find the change in length and the radius. So we determine the change in length, we also determine the change in radius. So how do we get to determine the change in length? So we are going to use, of course we know that change in length is related to shear, to tensile stress. Tensile stress is given by change in length over actual length. Do you have the tensile stress here? Okay, we don't have it there, but we are able to do that. So another thing that we know is tensile. I've just put something wrong here. This is stress. I thought I wrote a strain. So tensile stress is given by force over area. Now tensile strain, it is the strain which is the change in length over actual length. So we can determine the tensile stress and also the tensile strain at this point. But we also know Young's modulus. Young's modulus is given by tensile stress over tensile strain, giving us Young's modulus to be equal to force over area divided by, I should have written it down, but I can just say divided by tensile strain is change in length over actual length. And so this is also going to give us force. So if I change this to multiplication, this one is going to go on top and then that comes down. So that is going to be force multiplied by length over area multiplied by change in length. So let's get to make change in length to substitute the formula. So I'm going to cross multiply. So that is going to be E. This one here is area. E multiplied by area. And then change in length is going to be equal to force multiplied by length. So making change in length subject, change in length is going to be equal to force times length and then divided by Young's modulus times also that's the area. Okay, like that. Let me just get to write it perhaps. Okay, I just get to write it well on top so that we are going to have enough space. So I'm saying E is given by force over area divided by change in length over length, the actual one. So E is going to be force multiplied by length divided by area change in length. Crossing and multiplying, E area change in length is going to be equal to force times length, and the change in length is going to give us force multiplied by radius, multiplied by length divided by E multiplied by area. So let's see what we can substitute here. Do we have the force? Yes, we have got a force there. And what of the actual length? Yes, we have got it there. And then Young's modulus? Yes, we have it there. What of the area? Where is the area? Well, we know the radius, so we can obviously determine the area. Let's find the area first. And we've been told this is a cylindrical steel rod. So if it is in form of a cylinder, then the area of the top of a cylinder is simply a circle, and the area of a circle is given by pi r squared. And so that is going to be equal to pi. The radius we've been given as 0.5 centimeters. We get to convert that to meters. How? Just divide by 100. Okay, so 0.5 divided by 100, and then we get to square that and then multiply by pi. So that is given me 7.85 times 10 to the power negative 5 meters squared. And so the change in length is going to be equal to force, a force of 2 times 10 to the power 4, and then times the actual length, which is 2 meters, divided by Young's modulus, which is 200 times 10 to the power 9, and then times the area, which is 7.85 times 10 to the power negative 5. So this will give us a change of length in length being equal to 2.5 times 10 to the power negative 3 meters. Okay, so that is the change in length. Now the other part we are remaining with is to determine the change in radius. Now remember we mentioned of the Poisson's ratio at the very beginning. And what did we say about it? Well, we said that the Poisson's ratio given by mu is given by the lateral strain and then divided by lateral, sorry, not lateral, but that is linear strain. Now, how do we get to find the lateral strain? We said lateral strain is simply the strain that talks about the change in radius, and so that was mu is equal to, well, change in length, because change in radius, we said the radius always reduces, so it will be negative change in radius over actual radius, and then I'll say divided by a linear strain, that is change in length over actual length, and so this will also give us negative change in radius times length divided by radius times change in length. Okay, so here we can now just get to substitute the values that we have. And let me just get to make this on the substitute formula. I'm going to cross and multiply, so this is going to be negative change in r L is equal to mu and then r change in length. So I want to remain with only change in radius. We'll divide by negative L both sides, so that will be mu r change in length divided by negative L. Okay, so that will give us change in length is equal to, now what is mu, which is the Poisson's ratio? We've been given 0.25, and then the radius of the bulb is 0.5. Now converting that to meters, simply multiply it by 10 to the power negative 2 or divide it by 100, that's the same thing, and then multiplied by the change in length. We've already determined the change in length, that is 2.5 times 10 to the power negative 3, and then get to divide that by negative the actual length. The actual length, we can see that is a 2, and so that will give us a change in radius that is equal to negative 1.56 times 10 to the power negative 6 meters. So that is going to be the change in length. Another question here, a sphere of lead as a volume 0.5 cubic meters when placed in atmospheric pressure, and 1 Pascal is 10 to the power 5 Newton per meter squared approximately. The sphere is lowered to a particular depth in the ocean where the water pressure is 10 to the power 8 Newton per meter squared, which is the same as 1000 pascals. The bulk modulus of lead is given as 8 times 10 to the power 9 Newton per meter squared. What is the change in volume of the sphere? Well, we know bulk modulus. Bulk modulus is given by volumetric stress over volumetric strain. And volumetric stress is simply force over area. And we know that force over area is simply pressure. Now, this is not just pressure, we said at the beginning, because something subjected to the influence of the atmosphere, it has got a certain pressure. And then when you take it in the river, there will be a certain pressure also. So that is simply a change in pressure because it already has a pressure. And then divided by, now the volumetric strain let me say divided by like that, is given by negative change in volume over actual volume. We are putting negative because volume always reduces when you put something or you throw something in water because of the forces that are going to be acting on it. So bulk modulus is equal to, that will be negative change in pressure. The volume is going to go on top, and then the change in volume is going to come down because it's a division when we change to multiplication. So what is the change in volume? So let's make change on volume as up the formulae. So crossing and multiplying, that would be bulk modulus change on volume, that would be equal to negative change in pressure times volume, and change in volume therefore is going to be equal to negative change in pressure multiplied by initial volume and then divided by the bulk modulus, and that will give us negative change in pressure is final pressure minus initial pressure. So it is lower to a particular depth in the water where the pressure is this. So we are going to use the pressure that is in SI unit, that is Newton per meter squared. So that is 10 to the power 8, and then we remove the initial pressure, which was in pascals. I mean, not in pascals, but in Newton per meter squared. So that is 10 to the power 5. And then we multiply by the actual volume. Actual volume here, or the initial volume, that is 0.5. And then we are going to divide by the bulk modulus. The bulk modulus has been given there as 8 times 10 to the power 9. So now from here, what are we going to get? So let's get to write it here. Change in volume is going to be equal to, and we'll just get to subtract 10 to the power 8 minus 10 to the power 5. That is going to give us 9.99 times 10 to the power 7. So if we get to subtract these two, we'll get 9.99 times 10 to the power 7, and we multiply by 0.5 and then divide by what is in the denominator there. So that is going to give us a change in volume. Because there's a negative outside here, we shouldn't forget. The change in volume is always negative. That shows that there's a reduction in volume. So that will be negative 0.6, negative 6.2 times 10 to the power negative 3, and that will be meters to the power 3. Now that you found the first question, that is the change in volume. Now we go to the second one. Second one is saying, what is the relative density change? Well, what is relative density? Relative density is simply the density of a material divided by the density of a standard material. In this case, we're talking of the relative density change. So that will simply be the change in density and then by the original density. So for part B. So the first thing is, of course, we already know that there's a certain change in volume, and we've already determined, no, we've not yet determined, we've found it. So we found the change in volume, but what will be the final volume after this change gets to happen? So final volume is given by initial volume minus that change. But because the change is negative, we're only interested in the change, but not in the negative sign. So we're going to take absolute. Because if we get to subtract, the answer is going to be much bigger other than a small change. I mean, it is supposed to decrease in volume, but if we get to use this one the negative way it is, then it's going to be much bigger to show increment and not reduction in volume. So the initial volume was 0.5. The change in volume we already calculated in the previous question was 6.2 times 10 to the power negative 3. Of course, it was negative, but I've put it in absolute, so the sign has changed and it is now positive. And that is going to give us 0.4938 meters to the power 3. Okay. Now, we know that we want to find the relative density change. First, we need to find the density. So let me put an initial there. Of course, this shouldn't be P actually, it should be rho, meaning density. So let this be the initial pressure. I mean the initial density, and let this one be the final density. Now, how do we get to find the final density? Final density is going to be given by mass over volume, and this should be the final volume, just like the initial density should be given by mass over what? Initial volume. Okay, like that. Now we know the final volume, but do we know the, of course we know, yes, the mass. So what we are going to do here is, let me express this volume in terms of the initial volume. And how are we able to do that? So the final volume, we are going to divide it by the initial volume. This is what we call relative. It is final divided by the actual, just like density. Relative density is the density of a material divided by the actual density of a relative, I mean of a substance that you are using as reference point. So this is going to be equal to the final volume. We've seen it here, that is 0.4938. What was the initial volume? Well, the initial volume of this material is 0.5. And when we get to work out this one, we are going to find 0.9876. So if I want to make VF this up to the formula, so VF is going to be, I'm going to multiply this by this. So VF is going to be 0.9876 V initial. So that is going to be it. And this is going to give us mass, but where there is final volume, I'm going to put 0.9876 and then multiplied by initial volume. And I'll just rewrite this. This is going to be 1 over 0.9876, and then you have got mass over volume. And this will give us 1 over 0.9876, that will give us 1.0126, and mass divided by the actual volume. Of course, the mass of the object doesn't change whether at the end or at the beginning, so mass divided by the initial volume, that will give us initial density. So what we are finding is that the final density is simply 1.0126 times the initial density. So this is going to be the relative density. Relative density is simply the density of a material over the density of a reference material. Now this is simply a relative density change. So it is the density of the material after the change divided by the density of the material before the change. And another way we could just take this one is just to find the density. Final density is given by mass over final volume. And this is equal to, what was the mass here? Well, do you know the mass of this object? Not really. So just say mass over the final volume is 0.4938. And then the initial density is given also by mass over initial volume. What is the mass? We don't know. What is the initial volume? The initial volume is 0.5. And so relative density is the density after a change divided by the density before a change. So that would be P final over P initial. And that will be equal to, the final one is mass over 0.4938. And then divided by the initial one, it is mass over 0.5. And this is going to give us, these are going to swap directions, so that will be mass over 0.4938, and then it will be times 0.5 divided by m. So this m and this m is going to cancel out, so P final over P initial. Therefore P final over P initial is going to be equal to 0.5 divided by 0.4938, and that is going to give us 1.012. And we can simply cross multiply to just make P final subject the formula, and that gives us the same answer. So let's just get to look at the last question on this one. A 15 centimeters long tendon was found to stretch 3.7 meters by a force of 13.4 newtons. The tendon was approximately round with an average diameter of 8.5 millimeters. Calculate the Young's modulus of the tendon. Now, how do we get to work out this one? So the rest of the question we've done, we've already given the Young's modulus and the others done. Now we're just calculating the other quantities. So same, we know that for us to calculate the Young's modulus, we need to know the stress, which is the tensile stress over the tensile strain. And in this case, how do we get to find the stress? So let's calculate those. So the stress is given by the force divided by the area. And this is going to be equal to force. How do we get to find the area? Area is given by pi r squared. So the force here is 13.4. And then pi, the radius to stretch by. Okay, it was approximately round with a diameter of 8.5 millimeters. So we've been given a diameter. So we know that radius is simply half of the diameter. So we divide that value by 2. And that will give us a radius, which will be 8.5 over 2, and that is going to be 4.25. That is in millimeters. But we need to compare to the SI unit. We know that in 1 meter, we have got 1,000 millimeters. So this will cancel out with this one. And what are we going to find there? So that is going to be 0.00425. So this is going to be the radius, and that is what we're going to substitute, the 0.00425. And we get to square this. And let's see what we're going to find. So the area is going to give us 0.0005675 meters squared. So that is just the area. Now I haven't put what is on top there is 13.4. So what will be the stress? We've already determined the area. So 13.4 divided by that value which is in the denominator. So that is going to give us 236144.0817. This is going to be newtons per meter squared. That's a unit for stress. Now that we know the stress, what of the strain? Strain is given by change in length over actual length. And the change in length, a 15 centimeters tendon was found to stretch by 3.7 millimeters. So that is the change in length, 3.7. Now this one is given in millimeters. Let's compare to meters. We know that a milli is 10 to the power negative 3. Okay. And then divided by the actual length was given as 15 centimeters, and the cent is 10 to the power negative 2. In other words, we have got 100 centimeters in 1 meter. That is why we're multiplying by 10 to the power negative 3. And then we have got 1,000 millimeters in 1 meter. And this is going to give us 0.02467. Therefore, Young's modulus is going to be equal to stress 236,144.0817 divided by strain, which is 0.02467. Therefore, the Young's modulus is going to be 9.57 times 10 to the power 6 newtons per meter squared. Well, that is going to be it now for this video. Thank you so much for watching. Enjoy your day.